Alright, today we're going to have a look at the Physics Paper 4 theory paper, which is the extended paper. There we go. And this is for October-November 2018. The code is 0625/41, and this is for the Cambridge International Examination. Alright, let's begin.
Let's begin. Wait. What?
Question 1. A train of mass 5.6 times 10 to the 5 kilograms is at rest in a station. At time t equals 0, a resultant force acts on the train and it starts to accelerate. Figure 1.1 is the distance time graph for the train for the first 120 seconds. And there we go, there's our graph. We've got a distance time graph. Use figure 1.1 to determine the average speed of the train during the 120 seconds. Okay. Well, speed equals distance divided by time. Now we're being asked for the first 120 seconds, so the question is how far did it travel during those 120 seconds? And there we go, 120 seconds, it travels this far. This is 4,500, 4,600, 4,700, 4,800 meters. So let's put that into our calculation. So that's 4,800 meters divided by that 120 seconds. And that will give us a value of 40 meters per second. Remember the units, 40 ms -1. There we go, and the units are in the answer there. Question 2, or part 2. The speed of the train at time t equals 100 seconds. Alright, we've got a distance time graph. We're being asked to find the speed, so for that we need to calculate the gradient of the graph at time t equals 100 seconds. That's the action we have to perform, so let's look at the graph. Now, what we do in these situations is we draw a nice straight line that's the tangent to the curve. It looks like this might actually be a straight line anyway, and it is. There we go. Big old straight line. Excellent. Now we could just use the ruler to get a straight line, and that'd be absolutely fine. Make sure it's a straight line. We can then divide it into triangle shape. That's okay. So we could really just use a small triangle up around about here. But the bigger the triangle, the better. And what I've actually done, make things a bit easier, is I've drawn an absolutely enormous triangle between these 2 points, point 1 and point 2. There we go. So what I'll do is just get rid of these lines I've drawn, and then I'll draw our huge triangle. There we are, that's the first part. And there's the second part. Excellent. So now I'm just going to find the length of the individual sides. So this change in y that I have is 4,800 meters minus 0 meters, so it's actually 4,800 meters. This change in x that I have along the bottom axis, I'm going to say that's about 40 there, going up to 120, so this length is 120 seconds minus 40 seconds. That gives me a value of 80 seconds. So the gradient is then going to be change in y divided by change in x, which is 4,800 meters divided by 80 seconds. Let's write that into the question. And that gives me a value of 60 meters per second. There we go. Let's write that in, and of course remember the units. So the key point there is to draw the biggest triangle that you can that's a tangent to the line. We were lucky that entire section was a straight line, so we just worked off that. Right. Part 2. Describe how the acceleration of the train at time t equals 100 seconds differs from the acceleration at time t equals 20 seconds. Okay, let's draw up the graph again. Now let's look at what we can see. We can see here a straight line graph at the top. And that straight line means constant speed. And because it's a constant speed, the acceleration equals 0. Here, it's a curve, so that means the speed is increasing. And that means that the acceleration exists. and it's positive. There we go. Alright, so what do we know? Well, at time t equals 20 seconds, the acceleration exists, so it's bigger than 0, and it's positive. And of course, just to be clear here, how about we put in that? At time t equals 100 seconds, there is no acceleration, it's moving with a constant speed. And there we are. Okay, let's look at part B. B1. The initial acceleration of the train is 0.75 meters per second squared. Calculate the resultant force that acts on the train at this time. Okay, we've got an acceleration, we want a force, and we were given a mass earlier on in the question. So we're going to need our equation. Force equals mass times acceleration. Now let's put our value in for the mass. And if we come up here, we can see the mass, 5.6 times 10 to the 5 kilograms. So we can use that. So it's 5.6 times 10 to the power of 5 kilograms multiplied by 0.75 meters per second squared. And that should give us a pretty big value. There we go, that gives us 420,000 newtons. Alright, so we can write that as 4.2 times 10 to the 5 newtons. Quite a lot of power in there, a lot of force. And again, make sure you're remembering your units, very important. Now part 2, B2. At time t equals 120 seconds, the train begins to decelerate. State what is meant by deceleration. Now, deceleration is not negative acceleration. Deceleration means the speed is reducing. It's very important, that. And the reason that's important is because you can have negative velocity. Things can be going in the negative direction, in which case a negative acceleration would speed them up. So the speed is reducing. Deceleration means it's reducing. It's getting smaller and smaller. And if it decelerates until it stops, that makes sense as a statement. Question 2. Figure 2.1 shows a uniform plank, AB, of length 2 meters suspended from 2 ropes, X and Y. The weight W of the plank is 210 newtons, and that's labelled on there. The force in rope X is P. The force in rope Y is Q. State in terms of P the moment of force P about B. Alright. Well, what do we know? We know that moment equals force times distance. Specifically perpendicular distance to the pivot. But moment equals force times distance, so what do we have? So we want to find the moment of force P about B. Well, force P, that's the magnitude of it, it's P. And the distance is 1.5 meters from B. So here we are, force P, the distance between here and here is 1.5 meters. So that's just 1.5 times this value of the force P. So 1.5 P. Make sure that decimal point's nice and clear. Okay, let's look at the next bit. Calculate the moment W about P. Okay, so the moment of W about B. So let's find W. Here we are. W is the weight, and it's asking for the moment of W about B, so we want to know what this distance here is. W is from the centre of mass. It's the weight from the centre of mass or the centre of weight of the object, and it points directly down. What does that mean? Well, we've got a uniform plank, so it'll be in the middle. The plank is 2 meters long, so this distance here will be 1 meter. Alright, so the moment of W about B is just simply going to be 1 meter times 210 newtons. So force times distance, 1 meter times 210 newtons, and that will give me 210, oops, don't need an equal sign there, Newton meters. There we are. Now here we go, here I've got the units for moment, which is Newton meters. In fact, there you go. There's a reason why you have to be careful. State in terms of P. I didn't put the units in. Newton meters. Make sure you're writing those units in. Okay. Now calculate the force P. We know that when an object is in balance, the moment about any point has to equal 0. So what do we have? Well, the anti-clockwise moment must equal the clockwise moment. And if we look at our diagram, we're dealing with moments about this point here, which means that the weight W is anti-clockwise. It's an anti-clockwise moment, and force P up here is producing a clockwise moment. There we go. So they have to be equal to each other. That means that 210 Newton meters must be equal to 1.5 P Newton meters. Oops, capital N, there we are. So I divide 210 by 1.5 and I should get the value of P. There we go. Rearrange that for P. P is just 210 Newton meters divided by 1.5, which will give me a value of 140 Newton meters. And again, remember our units as we put it in. Part 3, the force Q. Okay, so we have to calculate the force Q. Let's look at that picture again. There we go. And what I'm going to do is I'm just going to erase all of the work I've put on there. There we go, and that should make it a bit clearer what I'm going to do. Okay, so we know that if it's balanced, then the clockwise moment and the anti-clockwise moment from any point should equal 0. What I'm going to do is I'm going to calculate the clockwise and the anti-clockwise moment by, let's say I'm going to use this point in the middle, W, here. Why am I going to use this point? Because force times distance, 210 times the distance of 0, gets rid of that problem altogether. That just vanishes. So that gives me a clockwise moment and an anti-clockwise moment. This one here is a clockwise moment. This one over here suddenly becomes the anti-clockwise moment. There we are. Alright, so the distances. Well, that's 1 meter, this is 0.5 meters. Between there and there. So choose points about W. Right, now as we looked at that before, that was 0.5 times P on one side, and on the other side it was, looking for Q, it was 1 meter times Q. Now I've got a value for P. I've got 140 Newton meters. So 0.5 times 140 equals 1.0 times Q. In fact, I can rearrange that straight away and that'll give me a value for Q. The force is then 70 newtons. So the force from Q should be 70 newtons. Right, and I just want to review this because I know a few people have difficulties with this idea. You can take the moment from any point. And what I'm going to do is I'm going to take the moment from some different points to show that it still works out. Right, so suppose I didn't take them about this point W. Suppose I took them about point P. There we go, let's just erase the mess that's there at the moment. There we are. If I take them about this point P over here, it'll be actually about that point there, then my force times distance, I've got my clockwise and my anti-clockwise. This is clockwise, this over here is anti-clockwise, and we're doing it about P. So let's look at the different bits involved. My force times distance from P is P times 0. From this one, the weight would be 210 newtons times 0.5 meters. That's 105 Newton meters. And if I come all the way over to Q, then I have the distance from P is 1.5 meters, and I've got Q in newtons times 1.5 meters, and that has to equal this value over here. They have to be the same because my clockwise and my anti-clockwise has to balance. So that tells me that Q times 1.5 equals 105 Newton meters. I divide both sides by 1.5. That tells me that Q is 105 Newton meters divided by 1.5, which will give me a value of 70 newtons. That's equals 1.5 meters. There we go. So I can take it from that point as well. But now, Okay, what if I don't want to use either of those points? Will it still work? Let's look at it. I'll take this rating off the board. Now what I'm going to do, I'm going to go crazy. Let's use A as our point. Now let's look what we have. We have an anti-clockwise moment here. We have a clockwise moment here. And another anti-clockwise moment up at the end in Q. Okay, so I'm going to take moments about A. I know the clockwise and the anti-clockwise moments have to be equal to each other. They're just in the opposite directions. So what does that tell me? Well, let's look at the clockwise moment. So the clockwise moment is 210 newtons multiplied by 1 meter, which is how far it is away, and that gives me 210 newton meters. That's how far away it is from A. That's 1 meter. So let's look at my anti-clockwise moments. So my clockwise moments are what, 210. My anti-clockwise moments over here are from P, and we worked out P, and P is 140 newtons upwards in this direction. There we go. I nearly said 140 newton meters. Of course not, it's 140 newtons. Well, let's look at P first. It's 140 times 0.5 meters. That's newtons times meters, so that'll give me 70 newton meters. And now I have another force from Q, which is Q multiplied by 2 meters. There we are. Okay, so let's look at that. 70 newton meters plus 2 meters times Q, they have to be equal. So I just subtract 70 from both sides, and what I get is 140 newton meters must be equal to 2Q, which means I divide both sides by 2 and I get 70 newton meters equals Q. Okay, so let's go down here and see we've still got the same answer. We tried it 3 different ways from 3 different points. I'll do a little bit of a video on that at some point, but it really doesn't matter where in space you take it from. If you have your balance beam much the same as that, there we go, here, you could take your pivot point over here. You will still get the same answer. So it's just about picking the choice that's easiest for you. Question 3. State what is meant by the principle of conservation of energy. Right, easy one. Energy is never created or destroyed, it only changes forms. There we are. B. Figure 3.1 shows a girl throwing a heavy ball. State the energy changes that take place from when the girl begins to exert a force on the ball until the ball hits the ground and stops moving. Right, well first of all you have the chemical potential energy stored in the muscles, in the girl's muscles. Then of course that becomes the kinetic energy of the ball, the movement energy of the ball, and that is converted to sound and heat as the ball lands on the ground and stops moving. So let's put that in. There we go. Let's look at the next part. The mass of the ball is 4 kilograms. The girl exerts a force on the ball for 0.6 seconds. The speed of the ball increases from 0 meters per second to 12 meters per second before it leaves the girl's hand. Calculate the momentum of the ball on leaving the girl's hand. Well, momentum is just mass times velocity. And it symbols that little p. It's 2 marks. I'm just going to write out the equation and write out the working out. Okay, so momentum is going to be mass times velocity. Mass is 4 kilograms and velocity is 12 meters per second. So it's 48 kilograms meters seconds negative 1, or 48 Newton seconds, which is another valid unit for momentum. In part 2, the average resultant force exerted on the ball. Okay, so the average force is given by the change in momentum divided by the change in time. So that's going to be the mass times the final velocity minus the mass times the initial velocity divided by the change in time. So that's 4 kilograms multiplied by 12 meters per second minus 4 kilograms multiplied by 0 meters per second, which of course 0 divided by change in time, which is 0.6 seconds. Okay, and what that's going to give me is 48 Newton seconds, or kilograms meters seconds, divided by 0.6 seconds, which gives me a value of 80 newtons. There we are, so that's my answer, 80 newtons. Remember, put in your units there. Okay, let's look at our next one. Question 4, figure 4.1 shows liquid in a cylinder. The depth of the liquid is 10 centimeters and the radius is 3 centimeters. The weight of the liquid in the cylinder is 2.5 newtons. Calculate the density of the liquid. Ooh, interesting. Well, density is given by mass divided by volume. We're given here the radius of the cylinder, not the area. So let's look for a cylinder. Let's draw this on the cylinder itself. So the volume equals the area times the height. Here, of course, we've got our area and we'd have our height here. Now the area, it's a circle, is just going to be pi r squared times the height, h. Okay, so let's put that in. Times h. There we are. So that's pi times 3 centimeters squared times our height, 10 centimeters. And that's 282.7 centimeters cubed. So we know that density equals mass over volume. We've got the value for the volume now. What do we do about the mass? Well, we're given that weight equals 2.5 newtons. That's not the mass, because weight is mass times gravity. So what we have to do is take 2.5 and divide it by gravity. The mass, in this case, 2.5 newtons, divided by the value for gravity, which is, of course, 10 meters per second squared. And that will give us a value of 0.25 kilograms. Now, in general, whenever you're dealing with density, there's two possibilities. You're going to end up with something either has the units kilograms per meter cubed or in grams per centimeter cubed. They're the two that tend to come up. Okay, so let's look at what we've got. We've got centimeters cubed over here and kilograms here. So let's change that to 250 grams. Now, for our volume that we have, we're about to do our final part of the calculation. So let's look at the stuff we have. We've got one significant figure there, two significant figures there. Let's complete that to 280 centimeters cubed. That gives us two significant figures. Now, we've got a situation where we can finish off our density. Density is mass over volume, which is then 250 grams divided by 280 centimeters cubed. That gives us our final answer there, 0.89 grams per centimeter cubed. That's my final answer there. Alright, so let's put that in, 0.89 grams per centimeter cubed. Got my units, got my two significant figures here, these are the two significant figures there, which comes from the one and two significant figures over in this area, and on the other side, two significant figures over there. So that's absolutely fine. Excellent. There we are. Right, figure 4.2 shows a device that measures the pressure of a gas supply. And there we go. Well, as you'll know from the video I did talking about barometers and manometers, this is what's known as a manometer. There we go. So state the name of the device, manometer. And that tells us the pressure difference between this side and this side. The difference H between two liquid levels is 2 centimeters. The density of a liquid is 800 kilograms per meter cubed. Calculate the difference in the pressure of the gas and atmospheric pressure. Well, pressure in a liquid, density times gravity times height. In that case, that's going to be 800 kilograms per meter cubed times 10 meters per second squared times, now look at the units there, centimeters. Here I'm dealing with meters cubed. So I want to be doing everything in meters. So 0.02 meters. There we are. That will give me the answer, 160 pascals. There we go. Part 3, a similar device with a tube of small cross-sectional areas connected to a gas supply at the same pressure. State and explain any effect on the value of H. And again, if you check out the video that I did on manometers and barometers, then you'll see that the pressure is based only on the height. It's not related to the area in that case. So what will happen is that the value of height will be exactly the same. So let's just write that down. Okay. So the first part, the height H will remain the same, and the second part, the cross-sectional area does not affect the height. And there we go. So the cross-sectional area does not affect the height difference of the liquid. Let's move on to the next question. Question 5. Alright, in the space below, draw a labelled diagram of the structure of a thermocouple thermometer. Include the device from which a reading is taken. Right. Okay, a thermocouple thermometer basically exists because if I take a piece of metal, it's, we put it in something that you know the temperature of, so I'll just put some ice in a beaker. There we go. We're not dealing with a high-class thermocouple thermometer here. It's just a little thing made in the lab. I've got a wire going to one side and another junction at the other side. I'm going to have another wire coming up here, and maybe I'll attach it to an ammeter or voltmeter. It doesn't really matter. I'll explain why in a second. Let's go with an ammeter, why not? Okay, so the way it works is a few years ago, a few centuries ago I think it was, someone noticed that if you put the temperature of a piece of wire, a wire at two different temperatures, you actually get a voltage across it. Now, if you take two different wires and put them in two different temperatures, you get a voltage across them. If those wires happen to be made of different materials, you get two different voltages across them. Let's do copper and nickel. Is nickel a good one? Doesn't matter, it's just another type of metal. So there's two different voltages across them, and the way to think of it a little bit is like this. You end up with, say, one cell attached to another cell. They're both trying to push voltage, if you like, around this way. Just so happens that the one at the bottom is so much bigger, there we go, it pushes current round in that direction. That's really all that's happening. So because we've got two different metals, we've got a situation where we've got one in ice, both of them, sorry, in ice over here, and a beaker, and the wires are connected at both sides. You know what, I'm going to label both of those wires nickel, there we go. And because of that, if you put this end into a heat that you want to heat this end, then you will get a current travelling around this circuit, this round circuit, which is related to the temperature. There we are. So those wires have been twisted together. And I'll label that both sides. And there we are, that's a rough model for a thermocouple thermometer. Excellent. Now, thermocouple thermometer is used to measure the temperature of the flame of a small candle. State two reasons why a thermocouple thermometer is suitable for this application. Well, number one, it doesn't take a lot of heat to heat it up. It's just a little wire, so it doesn't need a lot of thermal energy to change temperature, to heat up. And another one, well, it's suitable for high temperatures. Right, B, state and explain the effect on the sensitivity of a liquid in glass thermometer of reducing the diameter of the capillary tube. Ooh, right, well, what will happen there? I'll do a brief little drawing. So, what these ones are, it says a liquid in glass. what you've got is a bulb. As the temperature goes up, the liquid in here takes up more volume. And that means that maybe it moves from there to here. If this tube is thinner, then what will happen is the same change in volume will create a much bigger change in the level that it'll be visible at. Okay, so reducing the diameter of the capillary tube will increase the sensitivity. The small changes in temperature will have large changes in the level in the capillary tube. And increasing the volume of the liquid-filled bulb. Exactly the same effect at the end of the day. Change in temperature, same change in temperature, same proportional change in volume, but that means there's a lot more volume changing, which means again it's going to travel further up the tube. So it will increase the sensitivity as small changes in temperatures will have large changes in the level of the capillary tube. So let's put that in. So it'll increase the sensitivity, small changes in temperature will have large changes in the level of the capillary tube due to large changes in volume. Right, let's look at the next one. State 3 factors that determine the rate of evaporation of water. Step number 1, surface area. Of course, we've also got the temperature. And finally, whether there's a wind moving over the surface. Because while there's some molecules of water which are converting to gas, if they're sitting on top of the water, if you've got that vapor pressure, there's also some gas converting into water. If you have a breeze that carries that away, you remove that part of it, so there's a greater level of evaporation. B. A person climbs out of a swimming pool and stands in the open air. Explain why evaporation of the water from the surface of the person's body causes the person to feel cold. And that all comes down to this idea that what's actually escaping are molecules with higher than average energy. As they're escaping, the molecules that are left, the average energy decreases, which means the temperature decreases. So molecules with greater than average kinetic energy escape the liquid surface. The average kinetic energy of the remaining molecules decreases, and the liquid takes, or the water in this case, takes energy from its surroundings, which is the person. And because of that, the person feels cold. There we go. 7a. A laser produces a beam of monochromatic light. State what is meant by the term monochromatic. Well, that just means single colour. It's a single frequency or a single wavelength. There we go. So light of a single frequency, and you could put single colour or single wavelength. That should still get you the marks. B. A wave in air is incident on a glass block. Figure 7.1 shows the wave fronts at the air glass boundary. The arrow shows the direction of travel of the wave fronts. Okay. The wave undergoes reflection and refraction at the air glass boundary. On figure 7.1 draw the wavefronts of the reflected wave and the wavefronts of the refracted wave. First things first, let's do the reflected wave. Okay, so in general, when you've got a reflected wave coming in, that's a nice straight line, which is not really, but you get wave coming in like that, you can end up with a normal line every time that glides, and you should then find that the theta 1 is equal to theta 2. The angle it comes in with is equal to the angle it goes out with. So what we should have, if you like, is this idea of a normal line, and then over the other side we should have this ever increasing wave front bouncing backwards. There we are. And in an ideal world, maybe you're in the exam, so you probably want to do that. Maybe using a ruler. Yeah, just certainly use a ruler, but make sure you're drawing a little line in for the normal line just to make it easier on yourself. Okay, so there we go. That's my reflected wave. And part B was the wavefront of the refracted wave. Okay. So, what happens as it travels from air to glass is it slows down. Now as something goes from fast to slow, what happens is it bends towards the normal line. So if that's coming in at this angle, here it's going to bend a little bit more towards the normal line. So if the wavefronts are coming in, then what you'll see happen is this idea that as they're getting closer, they'll start to bend more towards that direction. So we should see there we go. A little bit tricky to do this, so what you want to do, pull out an eraser, and when you've got it where you think you want it, just try and, so there we go, not bad. Okay, let's see what's next. C. A transverse wave is produced in a long horizontal rope. The rope is much longer than the wavelength of the wave. In the space below, sketch a diagram to show the appearance of the rope as the wave passes along it. Label two important features of the wave. Okay, so here we've got a rope, we've got some wave moving along it. There we are, transverse wave, like so. And there we go. Now, got to label two features, so let's label the wavelength. And the amplitude. A vibrating source on a ship produces a sound wave that travels through the ocean. The wave produced is a longitudinal wave. Explain what is meant by the term longitudinal wave. Okay, the displacement of the particles is in the same direction as the motion of travel of the wave. Okay, so direction of motion of the particles is in the same direction as the wave travels. I can't see that getting more than 2 marks, so let's label something else about it. We have compressions and rarefactions. There we go. B. The frequency of a sound wave is 800 Hz. The speed of sound in air is 330 meters per second. State a typical value for the speed of sound in a liquid. Right. It's, well, we got a few things, haven't we? Solid, liquid, and gas. So for a gas, it's about, say, 300, 330 in the case of air. In the case of a liquid, it's about 1,000 meters a second. In the case of a solid, it's 5,000 meters a second. They're typical values. So in a liquid, about 1 kilometer a second, 1,000 meters per second. Using your value from B1, calculate the wavelength of the sound wave in the ocean. Alright, 2 marks here. So remember our units, and let's use our C equals F lambda. We want to find lambda. So that's going to be 1,000 meters per second. Oh, -1. It's not accelerating. Divided by the frequency of the sound wave, which is 800 Hz. Just seconds to -1. Doesn't matter too much. And that's 1.25 meters. There we go. Excellent. Figure 9.1 shows a symbol for a 12-volt battery. 2 lamps are connected in parallel with the battery. On figure 9.1, using the correct symbols, complete the circuit diagram. Okay, so they're in parallel. Always make sure these little lines are touching. You run the risk of losing marks if you don't. There we go. 2 lamps in parallel. One of these lamps has a resistance of 6 ohms. Calculate for this lamp the current. Okay. V equals IR. So I equals V over R, which will then give me, what's the voltage? 12 volts. 12 volts divided by 6.0 ohms. 2 significant figures for each, so that's 2.0 amps. The power, power equals IV, which is 2 times 12, that's 24 watts. Of course we could use I squared R, which is then 2 times 6, which will give me 24 watts again. The power of the other lamp is 36 watts, so it's different. Calculate the total energy delivered to this lamp in 20 hours. Alright, 36 watts, the energy delivered to this second lamp in a time of 20 hours. Well, normally we'd start by calculating the power, but in this case I've already given us the power. So energy equals power times time. Okay, so we have 36 watts times a time of 20 hours, but we don't measure that in hours, we measure it in seconds for our units here, because watts are joules per second. So 60 minutes in an hour, and 60 seconds in a minute. So there we go, we calculate that through and we get some crazy number, 2592123. There we go, joules. Now what do I have? I've got 2 significant figures, 2 significant figures, 2 significant figures, 2 significant figures. This should really have 2 significant figures, so that's 2.6 times 10. 1, 2, 3, 4, 5, 6 to the 6 joules. There we are. Question 10. A transformer consists of 2 coils of wire wound around a metal core. Figure 10.1 represents the transformer. A. State the name of the metal from which the core is made. Right. Now the core in a transformer is made of iron, same as the core in an electromagnet. And that's because it's magnetically soft. Not physically soft, if it hits you it will hurt, but it's magnetically soft. It doesn't hold its magnetism when the external magnetic field was removed. But it does adopt the external magnetic field when it's in one, so the magnetic field from the coils. B. The primary coil of the transformer is connected to the output of an AC generator which supplies an alternating current. 1. Explain why there is a voltage between the 2 terminals of the secondary coil. Okay, so what we have here, the alternating current in the primary coil creates an alternating magnetic field. It's transferred from using the iron core over to the secondary coil. So the secondary coil is essentially cutting through the magnetic flux, which creates a voltage in the secondary coil between the 2 terminals. That's what's happening. So there we go, just spent a few minutes right now. The alternating current in the primary coil creates an alternating magnetic field. The alternating magnetic field is transferred through the iron core and through the secondary coil. The secondary coil cuts the magnetic field, inducing voltage in the secondary coil. So that's what's occurring there. 2. There are 560 tons on a primary coil, 910 tons on a secondary coil of the transformer. The voltage between the 2 terminals of the secondary coil is 78 volts. Calculate the voltage supplied by the AC generator. Alright, so what we need for this then is our little equation. VVNN Right, the voltage in the primary divided by the voltage in the secondary is equal to the ratio of the tons in the primary, number of tons in the primary divided by number of tons in the secondary. Now we want to find the voltage supplied to the primary coil. So the voltage in the primary coil is equal to the voltage in the secondary coil multiplied by the number of turns in the primary divided by the number of turns on the secondary coil. Okay, so that gives us 78 volts multiplied by 560 tons. Oops, don't need to label tons. Divided by 910 tons. And that gives us the voltage supplied at the primary, which is 48 volts. There we go. C. Transformers are used to increase the voltage when electrical energy is transmitted in cables along long distances. Explain why the power losses in the cables are lower when the voltage is high. Okay, right. Basically what's happening is that the power loss in the cable is given by I squared R. Power transmitted is given by IV. So for the same power transmitted, if you increase the voltage, you decrease the current. Because power lost is I squared R, you decrease the power lost at a larger rate. Now how to fit that onto 3 lines is really the question. Okay, so there we go, I've given that a go. Power transmitted equals current times voltage. As the voltage increases, the current decreases for the same power transmitted. The power lost is given by I squared R. As the I decreases, the power lost also decreases. That should do just fine. 11a, figure 11.1 shows data about 9 elements. Carbon 14 is a radioactive isotope with a nucleon number of 14. It decays by emitting beta particles. Use any data you need from figure 11.1 to write down a nuclide equation for this decay. Alright, so we have to write down radioactive decay. Now we're told we get carbon 14. If I look at this section here, symbol, I've got carbon here. Carbon has a proton number of 6. I'm told it's carbon 14, so there we go. And let's get 14, a mass of 14. Alright, so I've got 14.6, that's going to decay. So that's going to decay with a beta particle. And beta particle is a charge of -1, and its mass is much smaller than a proton or a neutron, so we put 0 up there. Okay. And the question then becomes, what can I add -1 to, which mysterious number is equal to 6 minus 1? And the answer is, of course, 7. So if I look here, here we go, 7. So I'm going to end up with nitrogen, N. And the reason for that is that these numbers along the bottom are always conserved. The numbers along the top are actually always conserved as well, which tells me straight away that this number here is 14. 14 plus 0 equals 14. 7 minus 1 equals 6. There we are. So that's the equation I want to put down, and I want to put it down, obviously, under the question. So, 14.6 carbon decays via beta decay, charge of -1, mass of 0, and nitrogen, 14. There we are. That's it. B. A radioactive sample is placed close to a detector. The radioactive isotope in the sample has a long half-life. The detector records a count rate of 597 counts per second. Figure 11.2 shows the readings when the different materials are placed between the radioactive sample and the detector. Explain whether any alpha particles, beta particles, or gamma rays are emitted by the radioactive sample. So let's deal with this bit first. The detector records a count rate of 597, and then other materials are placed between them. If it's emitting alpha decay, or alpha particles, then they'll be stopped by a sheet of paper. If it's emitting beta particles, they'd be stopped by thin aluminium or aluminium. And the 597 is pretty close to 602, and it's pretty close to 598. So it looks like there's no change. So no alpha particles are being emitted. Why? Because the count rate is unchanged within the experimental accuracy. So no, the count rate is unchanged within experimental accuracy when the paper is placed between the source and the detector. Beta particles, exactly the same event. No, the count rate is unchanged within experimental accuracy when the aluminium is placed between the source and detector. So we have to write that out again. No. And gamma rays. Well, if we get gamma rays, they will be reduced by a thin piece of lead, and we can see here that the number's clearly reduced. 510, it was 600 or so, 597. So that's a big reduction. So gamma rays, yes, gamma rays are being produced. There we go. So yes, the count rate is diminished when a thin piece of lead is placed between the source and the detector. Alright, there we go. That's the end of that paper. So hopefully you found that useful. If you have, please feel free to like and subscribe. And if you've got anything you'd like me to have a look at, then please feel free to leave a comment in the section below. And, either way, have a great day.